In this session, we are going to discuss different types of final reduction drives, which is a topic in Unit 1 of the course Farm Tractors and Construction Equipments of 5th semester Automobile Engineering. In the last session, we have discussed about the introduction to final drive, different types of final drive reductions such as single reduction final drive, double reduction final drive, double speed, double reduction final drive. In this session, we are going to discuss about different types of hub reduction axles. In that, one is per gear reduction hub axle and another one is epicyclic gear reduction. So we shall go through this hub reduction axle with spur gears. You can see here, this is the axle shaft and here is the differential with crown and pinion as usual, and here there is another set of spur gear arrangement is provided. At the end of the axle shaft there is spur pinion and there is spur gear. This spur gear is mounted on stub shaft and the stub shaft carries the wheel hub. Therefore, one reduction takes place at the final drive of differential and another reduction takes place at the hub of the wheel. So here also double reduction is taking place. These spur gears are enclosed in an housing and they are operating in an oil bath. This arrangement has its own advantages. First of all, it provides more ground clearance or high ground clearance, which is very much required aspect for tractors. Second one is the axle shaft operates at low torque for the same power. You can see in this diagram, this is the axle shaft. These axle shaft are operating at lower torque compared to double reduction final drive, which we have discussed in the last session. There torque is subjected to the axle is subjected to more torque. But here only final drive reduction is provided at the differential end. That's why torque is increased only in one step and that torque is transmitted through axle shaft. But in the previous case, in the case of double reduction final drive, the torque is the gear reduction takes place in two stages in the previous case. That's why axle shaft, in that arrangement, axle shaft is subjected to high torque. But in this case, axle shaft is subjected to low torque because of single reduction at the differential. The another reduction is taking place at the wheel hub. That's why this axle shaft is operating at lower torque. Next advantage is increased tractive effort. The tractive effort increases because of the increase in gear ratio that you already know. This is the common advantage in all the arrangements, and this is the very important and main main requirement required. For this only we are providing different types of gear reductions. And another one is reduced stress on teeth of crown and pinion, because secondary reduction is taking place after the crown and pinion. That's why crown and pinion are operating at lower torque and they are subjected to reduced stress. Next, in this case we can calculate the gear ratios by using the simple gear ratio formula, as we have discussed in the last class. Same formula we can use by considering teeth on driven gears divided by teeth on driving gear, that is equal to speed of driving shaft divided by speed of driven shaft. Here this drive pinion is the driving gear and crown wheel is the driven gear. Spur pinion is the driving gear and spur gear is the driven gear. So that we can calculate the gear ratio, and we can calculate the amount of wheel speed and the torque multiplied everything by using the formulae what we have discussed in the last session. Next, another important types of arrangement. This is hub reduction axle with epicyclic gears. This type of arrangement is also used in different types of heavy commercial vehicles or heavy duty vehicles, military tankers, and also in tractors. This is the axle shaft. At the end of the axle shaft, sun gear is mounted. Around that planetary pinions. These planetary pinions are have a carrier. That carrier is attached to this wheel hub, whereas this ring gear is attached to the axle housing. At this end there is differential housing. Okay, how does it work? We shall see here. This is simple epicyclic gear train. This simple epicyclic gear train, it consists of sun gear. In our case, it is this sun gear is attached to the axle shaft end, whereas this planetary pinions mounted on their own pins of the planet carrier. This planet carrier is attached to the wheel hub. Sun gear is attached to the axle shaft, and this planetary pinions and planet carrier is attached to the wheel hub, whereas this ring gear is attached to the axle casing. This ring gear is stationary, whereas this sun gear is a driving gear, because to the axle shaft power is transmitted from the engine. Axle shaft is rotating, is the driving member, and therefore the sun gear is the driving member. Planet carrier is the driven member, whereas this ring gear is stationary. With the epicyclic gear train, if we want the output out of these three members, any one should be locked in order to get the output from this epicyclic gear train. Here the ring gear is locked to the axle housing. Ring gear is stationary, it is not revolving. So now sun gear is the driving member. So what happens here, you see, when the sun gear is the driving member, consider the sun gear is rotating in clockwise direction. When the sun gear is rotating in clockwise direction, these planetary pinions, they are rotating in anti-clockwise direction on their pins. All the planetary pinions are revolving in anti-clockwise direction. While they are rotating in anti-clockwise direction, since the ring gear is stationary, they walk around on the teeth of this stationary ring gear like this. So it is rotating. This planetary pinion is rotating in anti-clockwise direction, and it begins to walk on the teeth of stationary ring gear. So due to this, what happens, planetary carrier is also rotating in clockwise direction only. Sun gear is rotating clockwise, this planetary carrier is also rotating in clockwise. You can see here sun gear is rotating clockwise direction, planetary pinions are rotating in anti-clockwise direction about their pins, but these planetary pinions, they walk on the teeth of stationary ring gear. Therefore planet carrier is also rotating in clockwise direction. Axial shaft is rotating in clockwise direction, whereas this wheel hub is also rotating in clockwise direction. But the speed of carrier is always less than the speed of sun gear. It gives out certain gear ratio. Since it gives gear ratio, the wheel speed is decreased than this axial shaft. So let us consider how the speed is reduced and how we can calculate gear ratios. For these calculations, here are some notations. Omega s and omega c are the angular velocity of sun and planet carrier respectively in radians per second. Angular velocity, we know that angular velocity is rate of change of angular displacement. Any rotating member has angular velocity. Omega s is the angular velocity of sun wheel, omega c is the angular velocity of carrier. Vs and Vc are the linear velocity of sun and planet carrier in meter per second. Zs, teeth on sun gear, Zp, teeth on planetary pinions, Z or teeth on ring gears. Rs, radius of sun gear, Rp, radius of planetary pinion, Rr, radius of ring gear. We have a relationship between the linear velocity and angular velocity, that is linear velocity v equals angular velocity into r radius of the rotating member. By considering this relationship, we have here linear velocity of planet carrier is equal to angular velocity of planet carrier into radius, the effective radius of that planet carrier. This is radius of sun gear plus radius of planet pinion, planetary pinion. You can see in this diagram, from here to here, this is the radius of sun gear. From here to here, this is the radius of planetary pinion. Therefore, the angular velocity of this planet carrier can be calculated by omega c. Angular velocity is the planet carrier, angular velocity of the planet carrier is omega c multiplied by rs plus rp. By this we will get linear velocity. Linear velocity of planet carrier Vc equals omega c into rs plus rp. And then linear velocity of sun gear is equal to omega s into rs. Omega s is the angular velocity of sun gear, rs is the radius of sun gear. Again we have a relationship Vs equals 2Vc. Vs, that is linear velocity of sun gear is equal to twice the linear velocity of planet carrier. This relationship we can derive by considering a rolling circle on a straight line. Here compare the velocity of different points on the circle and the center of circle while it is rolling on a circle. If you consider the velocity of different points on circle and the center of circle, we can derive this relationship. So based on this relationship, here we are applying Vs equals 2Vc. Vs already we know, that is omega s into Rs, that is equal to twice omega c into Rs plus Rp. Now take the by taking ratio of omega s by omega c. Omega s by omega c, that is equal to 2 into rs plus rp by rs. Multiply this one, 2rs plus 2rp by rs equals 2rs plus rr minus rs. Instead of 2rp, we have written here rr minus rs. That you can easily find from this diagram. 2rp, so from here to here rp, from here to here rp, that means twice the radius, 2rp. This is 2rp, is it not? Rp plus rp gives 2rp, and here from here to here, this is radius of ring gear rr, and then from here to here, this is rs, radius of sun wheel. Rr minus rs gives 2rr. Rr minus rs gives 2rr. So instead of twice the radius of pinion is here. Once again I will explain. This is rs, and this one is the radius of sun wheel, and this one is the radius of ring gear rr. So rr minus rs is equal to 2rr. So instead of twice the 2rp, instead of writing 2rp, we can write rr minus rs. Yes, it is 2rp. So twice the radius of planetary pinion can be written as radius of ring gear minus radius of sun gear. So divided by rs. By simplifying this equation, we will get the gear ratio as 1 plus zr by zs, because we are getting here 1 plus rr by rs. Rr is directly proportional to number of teeth on ring gear. Rs is directly proportional to number of teeth on sun wheel. Therefore, we will get 1 plus zr by zs. Final gear ratio, we will get IF equals reduction in the epicyclic gear train into reduction in final drive. This ZC by ZD is the reduction in final drive. So finally we will get the speed of road wheel is equal to speed of propeller shaft divided by IF. That is, speed is decreased, and torque at the road wheel is multiplied by IF into torque at the propeller shaft. Hence, we are getting the multiplied torque and reduced speed. Next, multiple choice questions. The epicyclic gear train provides reverse speed when there are 4 options here. Out of these options, sun gear drives the ring gear, planet carrier is locked. Consider sun gear is rotating in clockwise direction. Let us come to this diagram. Sun gear is rotating in clockwise direction, planet carrier is fixed, then these planetary pinions are revolving in the fixed position in anti-clockwise direction, then they drive the ring gear in opposite direction. So we are getting the reverse speed with reduction gear. Next, second one, the epicyclic gear train provides direct speed when any two members are locked. When any two members are locked together, we are getting direct speed. Consider like that sun and planet carrier are locked together. Then if the sun gear is driving member, this whole unit is rotating as a single unit, including ring gear. Everything is rotating as a single unit. We are getting direct drive. 1:1. Next, the epicyclic gear is in neutral position when none of the members are locked. When none of the members are locked. Here you see that sun gear, suppose consider sun gear is driving gear. Here planet carrier is not locked and ring gear is also not locked. Then sun gear drives at that time. So since they are not locked, all are simply revolving, but power is not transmitted. The gear set is in neutral position. Double reduction axle reduces the stress on crown and pinion teeth. In case of double reduction axles, it decreases the stress on crown and pinion because of the secondary gear reduction. So thank you for watching this video session of final drive reduction. Thank you.